section 7.5, and we'll be multiplying and dividing radical expressions. A little bit about this in the previous section when you multiply radicals, but just to get a little more specific, when you're multiplying radicals, we multiply the outside terms. Next, you multiply the inner terms. We always simplify. They also have to have the same index in order to multiply them. Like we said in the last section, when you are adding or subtracting radicals, they have to have the same index and the same radicand. When you're multiplying radicals, they just have to have the same index. You multiply the outside numbers and you multiply the inside numbers separately. Let's just go through a few of these. My directions are just going to be to simplify. Say we have the square root of 11 times 5 minus the square root of 2. Five doesn't have a radical, so we're not going to do 5 times 11. The 11 is inside the radical. That only gets multiplied with other numbers that are inside the radical. So we're just going to do 5 times the square root of 11 minus the square root of 11 times the square root of 2 would be the square root of 22. It's inside the radical. You multiply it with other numbers inside the radical. Otherwise, if it's on the outside, you keep it on the outside. If we had 7 times the square root of 54 minus the square root of 24, 7 would be on the outside. So again, we just distribute like we would with a binomial or a polynomial. We get 7 square root of 54 minus 7 times the square root of 24. At this stage, what we want to do, you can't just distribute it. Let's look to simplify. So the square root of 54, is there a perfect square that goes into 54 that you guys can think of? 9 does? Is that the biggest one that goes in? I think so, right? So we could either simplify the square root of 54 as the square root of 9 times the square root of 6. That makes things a little bit faster for us. This would just be 7 times 3 root 6. You could have also made the prime factorization tree. What about 24? What's the biggest perfect square that goes into 24? 4, right? So this would just be the square root of 24 is the square root of 4 times the square root of 6 then. Or we'd have minus 7 times 2 root 6. 21 root 6 minus 14 root 6 gives us 7 root 6. That would be fully simplified. Instead of just multiplying by one term, what if we were going to multiply it by terms. So if we had 2 plus the square root of 3 times 1 plus the square root of 5. That's exactly right. Before, when we were talking about polynomials, we talked about the whole FOIL process where you multiply the first terms together. 2 times 1 is just 2. The outer terms together, 2 times the square root of 5 is just 2 root of 5. The inner terms would be 1 times the square root of 3. And then the last terms, 3 times root 5 is root 15. And that doesn't simplify anymore. So we're just going to leave that alone. But if we had the square root of 13 minus 2 to the second power. When I'm giving you exams, if anyone does this, taking full points off. It's a really big mistake. You're only allowed to distribute an exponent if it's multiplication or division on the inside. If it's addition, what we have to do is we do the square root of 13 minus 2 times itself. Let's go ahead and multiply this out. Square root of 13 times the square root of 16. We can multiply what's inside the radical. 13 times 13 is 169. Minus 2 square root of 13. Minus 2 square root of 13. Plus 4. Which would just be 13 minus 4 root 13. Plus 4, or 17 minus 4 root 13. Works similarly if we have say the cubed root. So if we had 4 plus square root of 3, or let's say 4 plus the cubed root of 7 times 4 minus the cubed root of 7. Uh, 4 times 4 is 16 minus 4 times the cubed root of 7 plus 4 times the cubed root of 7 minus the cubed root of 49. Minus 4 cubed root of 7 and plus 4 cubed root of 7. These are going to cancel. So 16 minus the cubed root of 49 would be our answer. You can't simplify the cubed root of 49. One more of these before we get to dividing. If we had the square root of r plus the square root of s times the square root of r minus the square root of s. After a while, you start seeing the same thing over and over again, right? It's the same process with different numbers or different letters. So r times r is r squared. R times s is rs. So we have minus square root of rs plus square root of rs minus the square root of s squared. have the same two terms with the sign differing, you're always going to have the two middle terms cancel. So we have minus square root of RS plus square root of RS. These cancel. And when we have the second root of R to the second, 2 over 2 is just 1. 2 over 2 for the S would just be S to the first. That would be the answer. Next topic I wanted to talk about is called rationalizing denominators. It's a little bit different. What we're going to do is focus first on monomial denominators. This is a little different than what you're used to. So let me explain how to do this. First step is we want to simplify. After we simplify, we multiply top and bottom of the fraction to make the denominators radicands power match the index. So for example, the direction for just to simplify or rationalize. If we had 5 divided by the square root of 3. What is the index? Power of the 3 is 1. In math, you are not allowed to have a radical in the denominator. So the way that we get rid of it is we want to make the index of 2 the same as the power of the radicand. So what we do is if we just multiply the top and bottom by the square root of 3, this gives us is 5 square root of 3 on top, and on the bottom we get the square root of 3 to the 2nd. That allows these things to just cancel. Just 5 over 3. You just don't want to have the same, you just don't want a radical in the denominator. So you multiply by whatever is going to match that power with the index. What if it was negative 3 over the square root of 18? First step is we want to simplify. So the square root of 18 is the same thing as square root of 9 times the square root of 2. So this would just be negative 3 over 3 square root of 2. And the problem is the square root of 2. It's not the 3 in front. The problem is the square root of 2. If we just multiply the top and bottom by the square root of 2, you get negative 3 square root of 2 over 3 times the square root of 2 to the 2nd. That enables us to cancel out that radical with the power, and we get negative 3 root 2 over 3 times 2, or negative 3 root 2 over 6. Which we could take one step further. Get negative root 2 over 2. Cancel out a factor of 3 on top and bottom. That would be the final answer. Yeah, so it's almost like if you had a question was, how did I do that last step? How did I simplify that? Yeah, it's just like if you had a regular fraction. 3 over 6 would be equals to 1 over 2. The question is, why wouldn't you want a radical in the denominator? And the answer is because that's just not an accepted form. Not my rule. It just makes people all over the world get the same answer. All right. When we're simplifying expressions, if you leave a radical in the denominator and somebody else doesn't, it's going to be hard to compare those two answers. So what we do is we just have a standard that says no radicals in the denominator anywhere in the world. So that way all our answers are always consistent. Does that make sense? It's just like, why wouldn't you leave an answer 6 over 2? Oh, if you just write 3, somebody in Japan's going to write 3, somebody in Europe's going to write 3. Does that make sense? Same idea. We want consistency, and that's a rule for consistency. Fair question. What if we had the cubed root of 2 over 3? We know that this is the same thing as the cubed root of 2 divided by the cubed root of 3. What do we have to multiply the top and bottom by to match the index with the denominator's power? We definitely need the cubed root of 3, but we want the power of the 3 to be to the third. So it looks like we have to bump it up by 2, right? If we multiply by the cubed root of 3 squared, that gives us a denominator of the cubed root of 3 to the third, which we can cancel out. We don't care about what's going on top. It's just 2 times 9, which is just 18. Let's try some with higher powers in the denominator, where we might have to simplify first. What if we had the square root of 200 to the 6th divided by y to the 7th? This is really like 4 problems in one. So what we want to do is let's simplify square root of 200. Let's simplify the square root of k to the 6th. Let's simplify the square root of y to the 7th. And then we'll try to what's called rationalize the denominator. Rationalize means just get the radical out of the denominator. So square root of 200 is the same thing as just the square root of 100 times 2, or 10 root 2. The square root of k to the 6th, how many groups of 2 would there be in 6? 3, so this is just k to the 3rd. And what about the bottom? How many groups of 2 are there in y to the 7th? There's 3 with 1 left over, right? So now let's write what this is fully simplified. This would be 10 e to the 3rd times the square root of 2 on top divided by y to the 3rd times the square root of y on the bottom. That's good. It's simplified, but we do have that square root on the bottom that we're not supposed to have. It doesn't matter what else there is. We're just kind of focused in on that square root of y. So we want to try to make the power of y be a 2. So it matches the index of the radical. If we just multiply by the square root of y on top and bottom, we get 10 k to the third square root of 2y divided by y to the third times the square root of y to the second. The second root of y to the second would cancel, and our final answer would be 10k to the third square root of 2y divided by y to the fourth. Y to the third times y is just y to the first. A couple more of these. Let's try the cubed root of 15 over 32. First step for these problems is, of course, you want to simplify. Cubed root of 15, there's no roots of 3 there. I do know that the cubed root of 32 is simplified. This would be 2 and 16. 16 is 2 and 8. 8 is 2 and 4, which is 2 and 2. So the cubed root of 32 would be 2 times the cubed root of 2 to the second. You don't want to write 4 because remember the whole goal here, we're trying to match the index with the power of the radicand. If you write 4, you're going to have 4 to the first and then want to multiply by 4 to the second. It's just going to get too big. So just keep it prime numbers. To finish this, we can multiply by the cubed root of 2 to the first, which gives us the cubed root of 30 divided by 2 times the cubed root of 2 to the third. Or cubed root of 30 over 2 times 2 is 4. One more of this before we shift to something a little bit different. What if we have the fourth root of 6y divided by w squared? It's the same thing as the fourth root of 6y divided by the fourth root of w to the second. What do we have to multiply to make the index match the power? Bump it up by 2 to get w to the fourth. The numerator would be the fourth root of 6y w to the second. The denominator would be the fourth root of w to the fourth. Cancel, giving us the fourth root of 6y to the second divided by w. more smaller topics to talk about before we close out tonight. We just got done talking about how to rationalize denominators if there's just one term in the denominator. What I want to do next is just talk about what to do if there's two terms in the denominator. So we'll talk about, let's call it binomial denominators. In order to do this, we multiply of the denominator. That word conjugate just means if the bottom is 2 plus square root of 3, we want to multiply by 2 minus the square root of 3. That's what conjugate means. You change the sign of the middle, and I'll explain why that is the way it is. Let's take an example, and the examples here are just going to ask us to simplify. Either simplify or rationalize. Either one of those verbs is saying the same thing. Please don't write this down. I just want to show you what happens if we try the same technique of the last type of problems. If you had a problem where it's 1 over 1 plus the square root of 3, what we would have done in the last type of problem is multiply top and bottom by the square root of 3 over square root of 3, right? That's what we would have done if it was a single term in the bottom. And what happens here is you just get square root of 3 over square root of 3 plus 3. So even though you got rid of the radical here, it shows up somewhere else. It's almost like, have you ever been to Chuck E. Cheese? Remember that from like being kids, or if you have kids? All right, it's like you whack a mole, you cancel out a radical, and something else pops up. And then you try to get rid of that by multiplying by the square root of 3. And it cancels out that radical, but you wind up with it on the other side. So you just can't get rid of it if you use that same technique. What we're going to do, you could write this down. I'll show you the correct way to handle this. You have 2 terms in the denominator. What we do is we outsmart it by multiplying by 1 minus square root of 3. This is called the conjugate. Conjugate just means we change the sign in the middle. Watch what happens if we do it this way. Top is just going to be 1 minus square root of 3. It doesn't matter what the top is. And the denominator would be 1 times 1 is 1 minus square root of 3 plus square root of 3 minus the square root of 3 times 3 is just 9. So you actually wind up canceling out the radical in the middle. You wind up with a positive and a negative radical. And it just turns into 1 minus square root of 3 over 1 minus 3. Or just simply 1 minus square root of 3 over negative 2. Sometimes I've seen people get rid of the negative in the denominator. So if you wanted to, you could also write this negative 1 plus root 3 over 2. I'll accept either one. Similarly, if there's radicals, like if we have the square root of 3 plus square root of 5 by the square root of 2 minus the square root of 7. It doesn't matter if there's one square root on the bottom, it doesn't matter if there's two. Using the conjugate has the same effect. So if we multiply by the square root of 2 plus square root of 7, divided by the square root of 2 plus square root of 7, doesn't matter what's on top. On top, we're just going to get the square root of 6 plus the square root of 21 plus the square root of 10 plus the square root of 35. The bottom is what matters. Using this conjugate, you get the square root of 4 plus the square root of 14 minus the square root of 14 minus the square root of 49. Think about it, it's kind of clever that it works out the way that it does. The square root of 14s are imperfect. You just wind up with 2 minus 7 on the bottom. 2 minus 7 is negative 5. Okay with this? I have a few more examples, but it's just the same thing with different numbers. I'm just going to leave it alone. What I wanted to do to finish is the last topic for tonight is just writing radical quotients in the list. I'll explain what that means. All this means is just simplifying. So if we had a problem like this, maybe 2 examples if we have time, actually just going to be to simplify. And the easiest way to do these is just to divide with monomials. So 24 minus 36 square root of 7 divided by 16. Fastest way to do this is to separate the fraction. So let's say this is just 24 over 16 minus 36 root 7 over 16. Reduce it. 24 over 16 is the same thing as 3 halves. 8 goes into 24 3 times, it goes into 16 twice. Six over 16 is just, well, 4 goes into 36 9 times. 4 goes into 16 4 times. So we're just simplifying fractions, we're reducing them. The last step is to try to combine them. So we have 2 separate fractions. The least common denominator would be 4. If we just multiply this fraction by 2 over 2, you wind up with 6 over 4 minus 9 root 7 over 4, giving us the final answer of just 6 minus 9 root 7 over 4. This is a fully simplified answer. Last problem tonight is 2x plus the square root of 32x squared divided by 6x. We'll do it the same way. The first step is 2x divided by 6x. And we'll also do the square root of 32 x squared divided by 6x. So it looks like we're going to have to do some simplifying. 2x divided by 6x, well, 2 divided by 6 is 3. So this is just 1/3. That would be the simplified fraction. Remember, x divided by itself is just 1. 2 divided by 6 is 1/3. Let's simplify the square root of 32 and the square root of x squared. What's the biggest perfect square that goes into 32? So this is square root of 16 times the square root of 2. And the square root of x to the second is just x to the 2 over 2. So the numerator would simplify to be 4 root 2 times x. Usually do is put the radical at the end. So 4 times x times square root of 2. Right, we'll just simplify here. 4 and 6 would just be 2/3. The x's would cancel. And then just to finish this, it would be 1 plus 2 root 2 over 3.